All right. Hello, everyone. My name is Alana Parey, and today I will be presenting on the pit to crack transition in stress corrosion cracking of type 304 stainless steels under marine exposure conditions. So as a little background, austenitic stainless steels are susceptible to localized pitting in marine environments. And stainless steel is currently being used for spent nuclear fuel dry cask storage. Containers that are intended for interim storage are beginning their relicensing period and must be reevaluated if they would like to continue using them. Canisters in overpacks may develop a chloride-rich brine on the surface. The overpacks can be seen in this image here. And the brine develops from accumulated dust that deliquesces on the surface. And sea salt from nearby environments is responsible for chloride presence. Brines form in droplets on the surface when the relative humidity and temperature on the surface exceeds the deliquescence relative humidity of a particular salt. So there's some previous work from White-Rich et al., who is a part of my research group, showing that there's a strong correlation between relative humidity and morphology under droplets. So these images below resulted from tests where sea salt particles were deposited on stainless steel coupons and then kept at the respective relative humidity shown at the same temperature. So on the left, we have our 40% relative humidity pits, and on the right, the 76% relative humidity pits. The 40% relative humidity pits seem to have, there's some sort of, there are lines through the bottom of the pits and some of them crosshatch. And that's a pretty common theme through all of these pits. Another thing that was noticed was that there is microcracking emanating from the edges of some of these pits going into the sample. Neither of these are present in the 76% relative humidity pits, which are more regular in shape, more generally ellipsoidal. So, yes. There is also found that there are significant compositional variations between brines at different relative humidities. In this case, you can see for the 40%, at the 40% relative humidity, the sodium chloride precipitates out of solution and is generally not, there's not much sodium in the brine, and so the brine becomes rich in magnesium chloride. When this happens, you can see in the 40%, this table lists all of the molal values of the concentrations of all the ions. Magnesium chloride dominates this 40% relative humidity, especially compared to the sodium chloride. And we can replicate the concentration of magnesium chloride present by using a 4.47 molar magnesium chloride solution. At 76%, the sodium chloride deliquesces into solution, leading to a sodium chloride-rich brine, which, as you can see here, the sodium dominates over the magnesium presence. And the magnesium, that's a 0.566 molar magnesium chloride solution, replicates that content, whereas for sodium, we can replicate it using a 5.22 molar solution. So the goal for these experiments is to determine why the difference in pit shape, pit morphology, and presence of microcracking occurs in marine atmospheric environments. These factors will contribute to the initiation of stress corrosion cracking. The hypothesis that this experiment is operating on is that species at lower relative humidities will exhibit more irregular pits, cross-hatching, and increased microcracking due to the presence of magnesium ions. So our generalized testing conditions, all of these tests will occur in full immersion conditions. Relative humidities will be represented by the brines that deliquesce at those relative humidities, and there will still be full immersion in those brines. Under full immersion, the cathodic area is maximized, which helps and will not curtail any pitting that we'll see on the surface. It will continue to grow. All tests happen at 35 degrees Celsius. All tests occur at, they have a ground surface finish, all cut from the same piece. And all of the tests were done on stainless steel 304L. Now here's a table summarizing the chloride equivalents and the indications of pittings in this far corner, if it pit or did not. As I mentioned previously, we're still doing tests with the 76% relative humidity seawater as well as the 40%. The 40% was done at 3 different intervals. We also did tests with the 5.22 molar sodium chloride, which again replicates the sodium content in the 76% relative humidity brines. There's the 0.566 molar magnesium chloride, which represents the magnesium content in the 76% relative humidity brines. There's a 2.61 molar, which that is the same amount of chloride present from if you were to use the 5.22 molar sodium chloride. So basically you're just dividing 5.22 in half. And then a test using the 4.47 molar magnesium chloride, which is the equivalent relative humidity. That's the 40%, and that's for magnesium chloride, because at 40%, magnesium chloride is dominant. So then looking through the resultant pitting, these tests here are all sodium chloride dominant, and they all exhibit similar morphologies. This top image, this is the 76% relative humidity in 2 weeks. And as you can see, pitting is still ellipsoidal in shape. And then below, these are the 3 sodium chloride tests. And as the exposure increases from 1 week to 2 weeks to 7 weeks, the pits continue to get larger. Something that can be seen here in the second 2 images is that pitting is starting to expand preferentially along the grinds lines. And the pits are starting to get a little less ellipsoidal, but generally they are following a general ellipsoidal shape. Next, here are the 40% relative humidity tests. As you can see, all of them generally exhibit microcracking and crosshatching. We start here, we have 1 week to 2 weeks to 4 weeks. And as you can see in this one has pretty significant microcracking and crosshatching that is occurring. All of these pits are also pitting. They're growing in the same direction as the grinds lines on the surface sample again. And moving down to the second week, the 2-week exposure, there is still some indication of the crosshatched morphology in the bottom, and there is also indication of the initiation of microcracking. In this image, it's not necessarily the clearest, but you can kind of see that in the middle, there's kind of a line that runs across the bottom, and there are a lot of crack-looking morphologies that kind of emanate out from that, and they appear to continue underneath the surface. And then moving on to the 4-week, the pits are, and here there is still microcracking, but it seems that they're growing wider, that maybe there's pitting occurring in them. These pits also generally have the crosshatching in the bottom. As time increases, generally the pits get larger with time, and it seems that the cracks aren't necessarily growing as fast as the pitting is. These tests are also other magnesium chloride dominant tests. This image here, this is the 0.566 molar magnesium chloride. The only one we got to pit was at 7 weeks. So that is this image. It's pretty ellipsoidal in shape, nothing too abnormal about it, very similar to sodium chloride tests. Moving on to the 2.61 molar, we got tests to pit at 2 weeks and 7 weeks. These pits, again, look generally pretty ellipsoidal in shape. The attack gets more aggressive as time goes on, but it doesn't deviate too much from that common ellipsoidal shape. It doesn't really look anything like the 40% relative humidity. And then this pit is the 4.47 molar mag chloride, and you can see at the bottom, there is that crosshatching starting to form at the bottom. However, there's not microcracking like was seen in the other tests at 40% relative humidity. So that's an equivalent magnesium chloride concentration. Microcracking to that scale was not seen in these samples. So generally, there might be crosshatching, but no microcracking was found in any of the just magnesium chloride tests so far. And just quickly, these tests were also carried out in stainless steel 304H, and generally they followed the same pit morphologies, they just had overall more aggressive pitting. So this was the 0.566 molar mag chloride, a 2.61 molar mag chloride, and a 5.22 sodium chloride. And all of these, again, you can tell in the sodium chloride, it's initiated from this more ellipsoidal pitting. You can also tell for this one picked up on, looks like some rough surface finish areas, and same with this one, they're all kind of ellipsoidal in shape, but they're just the pitting on average is more aggressive. So some of the conclusions reached, current research indicates that brine chemistry is the primary factor behind differences in morphology. This might explain why stainless steel experiences stress corrosion cracking more quickly under certain conditions, and it can determine under what conditions future SCC work will take place to observe more severe potential scenarios. Immersion tests under similar conditions with similar chemistries exhibit similar pit morphologies as seen from the images shown. Those are all grouped by similar chemistries, essentially. Also, magnesium ions influence pit morphology in short-term testing, but it has not been found to cause a severe microcracking seen in 40% relative humidity. So therefore, this microcracking must be promoted by some chemical species or chemical concentration present in the 40% relative humidity artificial seawater. These pH changes, there might be a pH change that occurs, maybe as a result of an addition of a chemical or changes in concentration. And it might be the effective pH that increases the microcracking susceptibility. Finally, in 40% relative humidity solutions, pitting seems to grow at a faster rate than microcracking, which may possibly be due to a lack of residual stress in the sample. So overall, magnesium chloride has an influence on pit morphology, but not on microcracking. In terms of future work, there were a few questions that are posed for the future, such as what is the role of residual stresses on pit morphology, specifically crosshatching? In the Weyrich et al. Paper, it is postulated that the presence of the crosshatching may be an effect of the surface roughness and any grinding that occurred on the surface could have induced residual stress, and that is yielding the crosshatching at the bottom of the pits. So that is something that has to be seen too. Another question is, how do pH and other minor species present in the brine affect the presence of microcracking? Again, that goes back to it's not just the magnesium chloride. There has to be something else in these solutions that is causing this microcracking. How does droplet size affect pit morphology? As mentioned, all of these tests were in full immersion conditions. So how will that change if smaller droplets are applied to the surface? How do differences in geometries and morphologies of the pit affect the crack initiation? Are there different geometries, different aspects of the pit that will cause it to crack more likely? And how will applying stress affect the continued initiation of microcracking? And that's just an overall generalized, it is stress corrosion cracking that we're looking at. So the application of more stress would likely cause the cracking to worsen, but as to how and the mechanisms is still something that has yet to be seen. All right, I'd like to thank you all for listening to my talk. Yeah, have a nice day.